High-dimensional data, meaning data that requires more than 2 or 3 dimensions to represent, can be difficult to interpret. One approach to simplification is to assume that the data of interest lie on an embedded nonlinear manifold within the higher dimensional space. If the manifold is of low enough dimension, the data can be visualized in the low-dimensional space. Below is a summary of some of the important algorithms from the history of manifold learning and nonlinear dimensionality reduction, NLDR. Many of these nonlinear dimensionality reduction methods are related to the linear methods listed below. Nonlinear methods can be broadly classified into 2 groups, those that provide a mapping, either from the high-dimensional space to the low-dimensional embedding or vice versa, and those that just give a visualization. In the context of machine learning, mapping methods may be viewed as a preliminary feature extraction step, after which pattern recognition algorithms are applied. Typically those that just give a visualization are based on proximity data, that is, distance measurements. Related linear decomposition methods. Independent component analysis, ICA. Principal component analysis, PCA, also called Karhunen-Loewe transform KLT. Singular value decomposition, SVD. Factor analysis. Applications of NLDR. Consider a dataset represented as a matrix, or a database table, such that each row represents a set of attributes, or features or dimensions, that describe a particular instance of something. If the number of attributes is large, then the space of unique possible rows is exponentially large. Thus, the larger the dimensionality, the more difficult it becomes to sample the space. This causes many problems. Algorithms that operate on high-dimensional data tend to have a very high time complexity. Many machine learning algorithms, for example, struggle with high-dimensional data. This has become known as the curse of dimensionality. Reducing data into fewer dimensions often makes analysis algorithms more efficient, and can help machine learning algorithms make more accurate predictions. Humans often have difficulty comprehending data in many dimensions. Thus, reducing data to a small number of dimensions is useful for visualization purposes. The reduced dimensional representations of data are often referred to as intrinsic variables. This description implies that these are the values from which the data was produced. For example, consider a dataset that contains images of a letter A, which has been scaled and rotated by varying amounts. Each image has 32x32 pixels. Each image can be represented as a vector of 1024 pixel values. Each row is a sample on a 2-dimensional manifold in 1024-dimensional space, a Hamming space. The intrinsic dimensionality is 2, because 2 variables, rotation and scale, were varied in order to produce the data. Information about the shape or look of a letter A is not part of the intrinsic variables because it is the same in every instance. Nonlinear dimensionality reduction will discard the correlated information, the letter A, and recover only the varying information, rotation and scale. The image to the right shows sample images from this dataset. To save space, not all input images are shown, and a plot of the 2-dimensional points that results from using a NLDR algorithm, in this case, manifold sculpting was used, to reduce the data into just 2 dimensions. By comparison, if PCA, a linear dimensionality reduction algorithm, is used to reduce this same dataset into 2 dimensions, the resulting values are not so well organized. This demonstrates that the high-dimensional vectors, each representing a letter A, that sample this manifold vary in a nonlinear manner. It should be apparent, therefore, that NLDR has several applications in the field of computer vision. For example, consider a robot that uses a camera to navigate in a closed static environment. The images obtained by that camera can be considered to be samples on a manifold in high-dimensional space, and the intrinsic variables of that manifold will represent the robot's position and orientation. This utility is not limited to robots. Dynamical systems, a more general class of systems, which includes robots, are defined in terms of a manifold. Active research in NLDR seeks to unfold the observation manifolds associated with dynamical systems to develop techniques for modeling such systems and enable them to operate autonomously. Manifold learning algorithms. Some of the more prominent manifold learning algorithms are listed below, in approximately chronological order. An algorithm may learn an internal model of the data, which can be used to map points unavailable at training time into the embedding in a process often called out-of-sample extension. Salmon's mapping. Salmon's mapping is one of the first and most popular NLDR techniques. Self-organizing map. The self-organizing map, SOM, also called Kohonen map, and its probabilistic variant generative topographic mapping, GTM, use a point representation in the embedded space to form a latent variable model based on a nonlinear mapping from the embedded space to the high-dimensional space. These techniques are related to work on density networks, which also are based around the same probabilistic model. Principal curves and manifolds. Principal curves and manifolds give the natural geometric framework for nonlinear dimensionality reduction and extend the geometric interpretation of PCA by explicitly constructing an embedded manifold, and by encoding using standard geometric projection onto the manifold. This approach was proposed by Trevor Hastie in his thesis, 1984, and developed further by many authors. How to define the simplicity of the manifold is problem-dependent, however, it is commonly measured by the intrinsic dimensionality and/or the smoothness of the manifold. Usually, the principal manifold is defined as a solution to an optimization problem. The objective function includes a quality of data approximation and some penalty terms for the bending of the manifold. The popular initial approximations are generated by linear PCA, Kohonen SOM, or autoencoders. The elastic map method provides the expectation maximization algorithm for principal manifold learning with minimization of quadratic energy functional at the maximization step. Autoencoders. An autoencoder is a feed-forward neural network which is trained to approximate the identity function. That is, it is trained to map from a vector of values to the same vector. When used for dimensionality reduction purposes, one of the hidden layers in the network is limited to contain only a small number of network units. Thus, the network must learn to encode the vector into a small number of dimensions and then decode it back into the original space. Thus, the first half of the network is a model which maps from high to low dimensional space, and the second half maps from low to high dimensional space. Although the idea of autoencoders is quite old, training of deep autoencoders has only recently become possible through the use of restricted Boltzmann machines and stacked denoising autoencoders. Related to autoencoders is the neuroscale algorithm, which uses stress functions inspired by multidimensional scaling and Salmon mappings, see below, to learn a nonlinear mapping from the high-dimensional to the embedded space. The mappings in neuroscale are based on radial basis function networks. Gaussian process latent variable models. Gaussian process latent variable models, GPLVM, are probabilistic dimensionality reduction methods that use Gaussian processes, GPS, to find a lower dimensional nonlinear embedding of high-dimensional data. They are an extension of the probabilistic formulation of PCA. The model is defined probabilistically and the latent variables are then marginalized and parameters are obtained by maximizing the likelihood. Like kernel PCA, they use a kernel function to form a nonlinear mapping, in the form of a Gaussian process. However, in the GPLVM the mapping is from the embedded, latent, space to the data space, like density networks and GTM, whereas in kernel PCA it is in the opposite direction. It was originally proposed for visualization of high-dimensional data but has been extended to construct a shared manifold model between two observation spaces. GPLVM and its many variants have been proposed specially for human motion modeling, e.g., back-constrained GPLVM, GP dynamic model, GPDM, balanced GPDM, BGPDM, and topologically constrained GPDM. To capture the coupling effect of the pose and gate manifolds in the gate analysis, a multi-layer joint gate pose manifolds was proposed. Curvilinear component analysis. Curvilinear component analysis, CCA, looks for the configuration of points in the output space that preserves original distances as much as possible while focusing on small distances in the output space, conversely to Salmon's mapping which focus on small distances in original space. It should be noticed that CCA, as an iterative learning algorithm, actually starts with focus on large distances, like the Salmon algorithm, then gradually change focus to small distances. The small distance information will overwrite the large distance information, if compromises between the two have to be made. The stress function of CCA is related to a sum of Wright-Bregman divergences. Curvilinear distance analysis. CDA trains a self-organizing neural network to fit the manifold and seeks to preserve geodesic distances in its embedding. It is based on curvilinear component analysis, which extended Salmon's mapping, but uses geodesic distances instead. Diffeomorphic dimensionality reduction. Diffeomorphic dimensionality reduction or Diffemap learns a smooth diffeomorphic mapping which transports the data onto a lower dimensional linear subspace. The method solves for a smooth time-indexed vector field such that flows along the field which start at the data points will end at a lower dimensional linear subspace, thereby attempting to preserve pairwise differences under both the forward and inverse mapping. Kernel principal component analysis. Perhaps the most widely used algorithm for manifold learning is kernel PCA. It is a combination of principal component analysis and the kernel trick. PCA begins by computing the covariance matrix of the M times N backslash display style M backslash times N M backslash times N matrix X backslash display style backslash math X backslash math X. C equals 1 MI equals 1 MXI XIT. Backslash display style C equals backslash frac 1 M backslash sum underscore I equals 1 M backslash math X underscore I backslash math X underscore I backslash maths T dot. C equals backslash frac 1 M backslash sum underscore I equals 1 M backslash math X underscore I backslash math X underscore I backslash maths T. It then projects the data onto the first k eigenvectors of that matrix. By comparison, KPCA begins by computing the covariance matrix of the data after being transformed into a higher dimensional space. C equals 1 MI equals 1 M phi, XI, phi, XI, T. Backslash display style C equals backslash frac 1 M backslash sum underscore I equals 1 M backslash phi, backslash math X underscore I, backslash phi, backslash math X underscore I, backslash maths T dot. C equals backslash frac 1 M backslash sum underscore I equals 1 M backslash phi, backslash math X underscore I, backslash phi, backslash math X underscore I, backslash maths T. It then projects the transformed data onto the first k eigenvectors of that matrix, just like PCA. It uses the kernel trick to factor away much of the computation, such that the entire process can be performed without actually computing phi, x, backslash display style backslash phi, backslash math x, backslash phi, backslash math x. Of course phi backslash display style backslash phi must be chosen such that it has a known corresponding kernel. Unfortunately, it is not trivial to find a good kernel for a given problem, so KPCA does not yield good results with some problems when using standard kernels. For example, it is known to perform poorly with these kernels on the Swiss roll manifold. However, one can view certain other methods that perform well in such settings, e.g., Laplacian eigenmaps, LLE, as special cases of kernel PCA by constructing a data-dependent kernel matrix. KPCA has an internal model, so it can be used to map points onto its embedding that were not available at training time. Isomap. Isomap is a combination of the Floyd-Warshol algorithm with classic multidimensional scaling. Classic multidimensional scaling, MDS, takes a matrix of pairwise distances between all points, and computes a position for each point. Isomap assumes that the pairwise distances are only known between neighboring points, and uses the Floyd-Warshol algorithm to compute the pairwise distances between all other points. This effectively estimates the full matrix of pairwise geodesic distances between all of the points. Isomap then uses classic MDS to compute the reduced dimensional positions of all the points. Landmark isomap is a variant of this algorithm that uses landmarks to increase speed, at the cost of some accuracy. Contagion maps. Contagion maps use multiple contagions on a network to map the nodes as a point cloud. In the case of the global cascades model, the speed of the spread can be adjusted with the threshold parameter t\displaystyle t\in\displaystyle t\in. For t equals 0 \displaystyle t equals 0 t equals 0, the contagion map is equivalent to the isomap algorithm. Locally linear embedding. Locally linear embedding, LLE, was presented at approximately the same time as isomap. It has several advantages over isomap, including faster optimization when implemented to take advantage of sparse matrix algorithms, and better results with many problems. LLE also begins by finding a set of the nearest neighbors of each point. It then computes a set of weights for each point that best describes the point as a linear combination of its neighbors. Finally, it uses an eigenvector-based optimization technique to find the low-dimensional embedding of points, such that each point is still described with the same linear combination of its neighbors. LLE tends to handle non-uniform sample densities poorly because there is no fixed unit to prevent the weights from drifting as various regions differ in sample densities. LLE has no internal model. LLE computes the barycentric coordinates of a point xi based on its neighbors xj. The original point is reconstructed by a linear combination, given by the weight matrix Wij, of its neighbors. The reconstruction error is given by the cost function E, W. E, W, equals ixijwijxj2 \displaystyle E, W, equals \sum_i\mathf_x_i _mathf_j\mathf_j mathf2e, W, equals \sum_i\mathf_x_i-mathf_j\mathf2. The weights which refer to the amount of contribution the point xj has while reconstructing the point xi. The cost function is minimized under two constraints. A. Each data point xi is reconstructed only from its neighbors, thus enforcing Wij to be 0 if point xj is not a neighbor of the point xi, and b. The sum of every row of the weight matrix equals 1. JWIJ equals 1 \sum_j\mathfw_ij equals 1 \sum_j\mathfw_ij equals 1. The original data points are collected in a d-dimensional space, and the goal of the algorithm is to reduce the dimensionality to d such that dd. The same weights which that reconstructs the ith data point in the d-dimensional space will be used to reconstruct the same point in the lower d-dimensional space. A neighborhood-preserving map is created based on this idea. Each point xi in the d-dimensional space is mapped onto a point y in the d-dimensional space by minimizing the cost function. C, y, equals iyijwij2 backslash display style C, y, equals backslash sum underscore I backslash math y underscore I dash backslash sum underscore j backslash math w underscore ij backslash math y underscore j backslash maths 2 C, y, equals backslash sum underscore I backslash math y underscore I dash backslash sum underscore j backslash math w underscore ij backslash math y underscore j backslash maths 2. In this cost function, unlike the previous one, the weights which are kept fixed and the minimization is done on the points y to optimize the coordinates. This minimization problem can be solved by solving a sparse nxn eigenvalue problem, n being the number of data points, whose bottom d non-zero eigenvectors provide an orthogonal set of coordinates. Generally the data points are reconstructed from k nearest neighbors, as measured by Euclidean distance. For such an implementation the algorithm has only one free parameter k, which can be chosen by cross-validation. Laplacian eigenmaps. Laplacian eigenmaps uses spectral techniques to perform dimensionality reduction. This technique relies on the basic assumption that the data lies in a low-dimensional manifold in a high-dimensional space. This algorithm cannot embed out of sample points, but techniques based on reproducing kernel Hilbert space regularization exist for adding this capability. Such techniques can be applied to other nonlinear dimensionality reduction algorithms as well. Traditional techniques like principal component analysis do not consider the intrinsic geometry of the data. Laplacian eigenmaps builds a graph from neighborhood information of the data set. Each data point serves as a node on the graph and connectivity between nodes is governed by the proximity of neighboring points, using e.g. the k-nearest neighbor algorithm. The graph thus generated can be considered as a discrete approximation of the low-dimensional manifold in the high-dimensional space. Minimization of a cost function based on the graph ensures that points close to each other on the manifold are mapped close to each other in the low-dimensional space, preserving local distances. The eigenfunctions of the Laplace-Beltrami operator on the manifold serve as the embedding dimensions, since under mild conditions this operator has a countable spectrum that is a basis for square integrable functions on the manifold, compared to Fourier series on the unit circle manifold. Attempts to place Laplacian eigenmaps on solid theoretical ground have met with some success, as under certain non-restrictive assumptions, the graph Laplacian matrix has been shown to converge to the Laplace-Beltrami operator as the number of points goes to infinity. MATLAB code for Laplacian eigenmaps can be found in Algorithms and the PhD thesis of Belkin can be found at The Ohio State University. In classification applications, low-dimension manifolds can be used to model data classes which can be defined from sets of observed instances. Each observed instance can be described by two independent factors termed content and style, where content is the invariant factor related to the essence of the class and style expresses variations in that class between instances. Unfortunately, Laplacian eigenmaps may fail to produce a coherent representation of a class of interest when training data consist of instances varying significantly in terms of style. In the case of classes which are represented by multivariate sequences, structural Laplacian eigenmaps has been proposed to overcome this issue by adding additional constraints within the Laplacian eigenmaps neighborhood information graph to better reflect the intrinsic structure of the class. More specifically, the graph is used to encode both the sequential structure of the multivariate sequences and, to minimize stylistic variations, proximity between data points of different sequences or even within a sequence, if it contains repetitions. Using dynamic time warping, proximity is detected by finding correspondences between and within sections of the multivariate sequences that exhibit high similarity. Experiments conducted on vision-based activity recognition, object orientation classification and human 3D pose recovery applications have demonstrated the added value of structural Laplacian eigenmaps when dealing with multivariate sequence data. An extension of structural Laplacian eigenmaps. Generalized Laplacian eigenmaps led to the generation of manifolds where one of the dimensions specifically represents variations in style. This has proved particularly valuable in applications such as tracking of the human articulated body and silhouette extraction. Manifold alignment. Manifold alignment takes advantage of the assumption that disparate data sets produced by similar generating processes will share a similar underlying manifold representation. By learning projections from each original space to the shared manifold, correspondences are recovered and knowledge from one domain can be transferred to another. Most manifold alignment techniques consider only two data sets, but the concept extends to arbitrarily many initial data sets. Diffusion maps. Diffusion maps leverages the relationship between heat diffusion and a random walk, Markov chain. An analogy is drawn between the diffusion operator on a manifold and a Markov transition matrix operating on functions defined on the graph whose nodes were sampled from the manifold. In particular, let a data set be represented by x equals omega rd backslash display style backslash math x equals backslash in backslash omega backslash subset backslash math rd backslash math x equals backslash in backslash omega backslash subset backslash math rd. The underlying assumption of diffusion map is that the data, although high-dimensional, lies on a low-dimensional manifold of dimensions d backslash display style backslash math d backslash math d dot x represents the data set and let mu backslash display style backslash mu represent the distribution of the data points on x. In addition to this, let's define a kernel which represents some notion of affinity of the points in x. The kernel k backslash display style backslash math at k backslash math at k has the following properties: k x y equals k y x backslash display style k x y equals k y x comma backslash comma k x y equals k y x comma backslash. K is symmetric. K x y greater than or equal to 0x, y, k backslash display style k, x y, backslash k 0 backslash k to add backslash for all x y k k, x y, backslash k 0 backslash k to add backslash for all x y k. K is positivity preserving. Thus one can think of the individual data points as the nodes of a graph and the kernel k defining some sort of affinity on that graph. The graph is symmetric by construction since the kernel is symmetric. It is easy to see here that from the tuple xk one can construct a reversible Markov chain. This technique is fairly popular in a variety of fields and is known as the graph Laplacian. The graph k equals xe can be constructed, for example, using a Gaussian kernel. Kij equals exixj22 slash sigma 2 if xixj0 otherwise backslash display style k underscore ij equals backslash begin cases e dash backslash x underscore ix underscore j backslash underscore 22 slash backslash sigma 2 and backslash text if x underscore I backslash sim x underscore j backslash 0 and backslash text otherwise backslash end cases k underscore ij equals backslash begin cases e dash backslash x underscore ix underscore j backslash underscore 22 slash backslash sigma 2 and backslash text if x underscore I backslash sim x underscore j backslash 0 and backslash text otherwise backslash end cases. In this above equation xixj backslash display style x underscore I backslash sim x underscore j x underscore I backslash sim x underscore j denotes that xi backslash display style x underscore I is a nearest neighbor of xj backslash display style x underscore j x underscore j. In reality, geodesic distance should be used to actually measure distances on the manifold. Since the exact structure of the manifold is not available, the geodesic distance is approximated by Euclidean distances with only nearest neighbors. The choice sigma backslash display style backslash sigma modulates our notion of proximity in the sense that if xij2 sigma backslash display style backslash x underscore I x underscore j backslash underscore 2 backslash gg backslash sigma backslash x underscore I x underscore j backslash underscore 2 backslash gg backslash sigma, then kij equals 0 backslash display style k underscore ij equals 0 k underscore ij equals 0, and if xij2 sigma backslash display style backslash x underscore I x underscore j backslash underscore 2 backslash ll backslash sigma backslash x underscore I x underscore j backslash underscore 2 backslash ll backslash sigma, then kij equals 1 backslash display style k underscore ij equals 1 k underscore ij equals 1. The former means that very little diffusion has taken place, while the latter implies that the diffusion process is nearly complete. Different strategies to choose sigma backslash display style backslash sigma can be found in. If k backslash display style kk has to faithfully represent a Markov matrix, then it has to be normalized by the corresponding degree matrix d backslash display style dd. P equals d1k. Backslash display style p equals d minus 1k backslash comma p equals d minus 1k backslash. P backslash display style pp now represents a Markov chain. P, xi, xj, backslash display style p, x underscore I x underscore j, p, x underscore I x underscore j, is the probability of transitioning from xi backslash display style x underscore I to xj backslash display style x underscore j in one time step. Similarly, the probability of transitioning from xi backslash display style x underscore I to xj backslash display style x underscore j in t time steps is given by pt, xi, xj, backslash display style pt, x underscore I x underscore j, pt, x underscore I x underscore j. Here pt backslash display style pt is the matrix p backslash display style pp multiplied to itself t times. Now the Markov matrix p backslash display style pp constitutes some notion of local geometry of the data set X. The major difference between diffusion maps and principal component analysis is that only local features of the data is considered in diffusion maps as opposed to taking correlations of the entire data set. K backslash display style kk defines a random walk on the data set, which means that the kernel captures some local geometry of data set. The Markov chain defines fast and slow directions of propagation, based on the values taken by the kernel, and as one propagates the walk forward in time, the local geometry information aggregates in the same way as local transitions, defined by differential equations, of the dynamical system. The concept of diffusion arises from the definition of a family diffusion distance dt backslash display style d underscore tt n backslash display style underscore t backslash in n underscore t backslash in n. dt2, x, y, equals pt, x, pt, y, 2 backslash display style d underscore t2, x, y, equals p underscore t, x backslash dot, p underscore t, y backslash dot, 2d underscore t2, x, y, equals p underscore t, x backslash dot, p underscore t, y backslash dot, 2. For a given value of t dt backslash display style d underscore t defines a distance between any 2 points of the data set. This means that the value of dt, x, y, backslash display style d underscore t, x, y, d underscore t, x, y, will be small if there are many paths that connect x to y and vice versa. The quantity dt, x, y, backslash display style d underscore t, x, y, d underscore t, x, y, involves summing over of all paths of length t, as a result of which dt_d_t_t is extremely robust to noise in the data as opposed to geodesic distance. dt_d_t takes into account all the relation between points x and y while calculating the distance and serves as a better notion of proximity than just Euclidean distance or even geodesic distance. Hessian locally linear embedding, Hessian LLE. Like LLE, Hessian LLE is also based on sparse matrix techniques. It tends to yield results of a much higher quality than LLE. Unfortunately, it has a very costly computational complexity, so it is not well suited for heavily sampled manifolds. It has no internal model. Modified locally linear embedding, MLLE. Modified LLE, MLLE, is another LLE variant which uses multiple weights in each neighborhood to address the local weight matrix conditioning problem which leads to distortions in LLE maps. MLLE produces robust projections similar to Hessian LLE, but without the significant additional computational cost. Relational Perspective Map. Relational Perspective Map is a multidimensional scaling algorithm. The algorithm finds a configuration of data points on a manifold by simulating a multi-particle dynamic system on a closed manifold, where data points are mapped to particles and distances, or dissimilarity, between data points represent a repulsive force. As the manifold gradually grows in size, the multi-particle system cools down gradually and converges to a configuration that reflects the distance information of the data points. Relational Perspective Map was inspired by a physical model in which positively charged particles move freely on the surface of a ball. Guided by the Coulomb force between particles, the minimal energy configuration of the particles will reflect the strength of repulsive forces between the particles. The Relational Perspective Map was introduced in. The algorithm firstly used the flat torus as the image manifold, then it has been extended, in the software VisuMap, to use other types of closed manifolds, like the sphere, projective space, and Klein bottle, as image manifolds. Local tangent space alignment. LTSA is based on the intuition that when a manifold is correctly unfolded, all of the tangent hyperplanes to the manifold will become aligned. It begins by computing the k-nearest neighbors of every point. It computes the tangent space at every point by computing the d-first principal components in each local neighborhood. It then optimizes to find an embedding that aligns the tangent spaces. Local multidimensional scaling. Local multidimensional scaling performs multidimensional scaling in local regions, and then uses convex optimization to fit all the pieces together. Maximum variance unfolding. Maximum variance unfolding was formerly known as semi-definite embedding. The intuition for this algorithm is that when a manifold is properly unfolded, the variance over the points is maximized. This algorithm also begins by finding the k-nearest neighbors of every point. It then seeks to solve the problem of maximizing the distance between all non-neighboring points, constrained such that the distances between neighboring points are preserved. The primary contribution of this algorithm is a technique for casting this problem as a semi-definite programming problem. Unfortunately, semi-definite programming solvers have a high computational cost. The landmark MVU variant of this algorithm uses landmarks to increase speed with some cost to accuracy. It has no model. Nonlinear PCA. Nonlinear PCA, NLPCA, uses backpropagation to train a multilayer perceptron, MLP, to fit to a manifold. Unlike typical MLP training, which only updates the weights, NLPCA updates both the weights and the inputs. That is, both the weights and inputs are treated as latent values. After training, the latent inputs are.
Please subscribe and thanks for watching.